Industrial facilities depend on pumps to keep fluids flowing through piping. One basic type of pump is called a positive displacement pump. There are many different kinds of positive displacement pumps, and they move fluid in different ways. To keep the positive displacement pumps in your facility working properly, you need to have a basic understanding of how they operate and how to perform maintenance on them. A reciprocating positive displacement pump uses the back and forth or reciprocating movement of components such as pistons, plungers, or diaphragms to move fluid. One common type of reciprocating pump is the piston pump, represented here. Its main components are a cylinder, which is located inside a casing, a piston, a connecting rod, and two valves, a discharge valve, and a suction valve. The connecting rod connects the piston to devices that move the piston back and forth. When the piston moves back on the suction stroke, it reduces the pressure inside the cylinder. The reduced pressure closes the discharge valve, opens the suction valve, and draws fluid into the cylinder. When the piston moves forward on the discharge stroke, it exerts a force on the fluid that increases its pressure. The increased pressure closes the suction valve, opens the discharge valve, and pushes the fluid out of the pump. At the end of the second stroke, the piston is in its initial position and the cycle begins again. Basically, the piston draws fluid into the cylinder and then positively displaces it. In other words, the piston takes the place of the fluid. The pressure of the piston pressing against the fluid gives the fluid the pressure it needs to move through the discharge piping. The plunger pump and the piston pump that we've looked at are both simplex pumps. They're simplex pumps because they each have only one piston or plunger. A simplex pump has a limited capacity. These pumps are single-acting pumps as well. That's because fluid is admitted on one part of the reciprocating movement and discharged on the other part. This creates a very uneven pumping action and the fluid is discharged in spurts. One way to help even out the pumping action associated with a single-acting pump is to use a double-acting pump. Double-acting pumps are designed so that each part of the reciprocating movement acts to both draw fluid into the pump and force fluid out of the pump. Here's an illustration of a simplex double-acting piston pump. It has a cylinder that contains a single piston, a discharge manifold that contains two discharge valves, and a suction manifold that contains two suction valves. When the piston moves to the left, the increased pressure on the left side closes the suction valve and opens the discharge valve on that side. At the same time, the reduced pressure on the right side closes the discharge valve and opens the suction valve on the right side. On the next stroke, the piston moves to the right, reducing the pressure on the left side of the piston and increasing the pressure on the right side. This closes the discharge valve and opens the suction valve on the left side, and opens the discharge valve and closes the suction valve on the right side. So during each stroke of a double-acting pump, fluid is forced out. The result is a smoother, more continuous discharge than you get from a single-acting pump. To overcome the capacity limitation of a pump that has a single piston or a single plunger, some pumps have two pistons or two plungers. These pumps are called duplex pumps. This duplex pump has two pistons that alternate their movements. It operates like two single-piston or simplex pumps that are side by side. Each portion of a duplex pump can be double-acting, as in this example, or single-acting. In either case, the strokes are mechanically timed to provide the smoothest possible discharge. Now is a good time to try a question on reciprocating positive displacement pumps. A rotary positive displacement pump uses the rotating motion of components such as screws, gears, lobes, and vanes to move fluid. In this part, we'll look at several examples of rotary pumps. One common type of rotary pump is a single screw or progressive cavity pump. The screw, or rotor, is located inside a casing, and it's connected to a driver. As the screw rotates, cavities form between the casing and the screw. These cavities move or progress toward the pump's discharge as the screw rotates, carrying the fluid along. Progressive cavity pumps are especially useful for moving extremely thick fluids, such as sludges and gels, since they can move these fluids without clogging. Another type of screw pump is the two-screw pump that's represented here. One of the screws is attached to a shaft that is coupled to the pump's driver. This screw is the driver screw. It's sometimes called the power screw. Power is transmitted from the driver screw to the other screw, which is the idler screw, through a set of timing gears. Fluid that enters the pump is directed toward both ends of the casing and is trapped between the casing and the screws as the screws rotate. The fluid is moved from both ends of the pump toward the center, which is also the pump's discharge. The force that is exerted by the rotating screws pushes the fluid out of the pump and through the discharge piping. Two other types of rotary pumps use gears to move fluid. One is an external gear pump, and the other is an internal gear pump. A type of pump that's similar to a gear pump is a lobe pump. This lobe pump has two rotors. Each rotor has two lobes that move fluid through the pump. Depending on their design, a lobe pump can have 2, 3, or 4 lobes on each rotor. Some rotary pumps use vanes instead of gears or lobes to positively displace fluid. An example is this sliding vane pump. It has vanes that can slide in and out of the rotor. The next two rotary pumps we're going to look at are called flexible member pumps. These pumps employ flexible parts to move fluids. One uses flexible vanes, and one uses a flexible tube. In this topic, we describe the basic operation of various types of reciprocating pumps and rotary pumps. Take some time now to try a couple of practice questions. A pump overhaul begins the same way that any other type of mechanical maintenance work begins, with careful preparation. A good first step is to check the pump manufacturer's instruction manual to make sure that you're familiar with the pump specifications and any special instructions pertaining to the overhaul. Also, check your company's procedures. It's important to follow those procedures exactly without making any unauthorized changes or taking any shortcuts. In addition, you should follow all applicable safety precautions that are associated with the work. For example, make sure that you have the appropriate protective gear. If you know ahead of time what replacement parts you're going to need, order them far enough in advance to have them available when the overhaul begins. Part numbers and other information can be found in the manufacturer's instruction manual. If the pump is large, you may also need rigging equipment, such as a chain hoist or a come-along. And you'll need a pair of V-blocks to support each of the pump's rotors while the rotor is being inspected after the pump is disassembled. After you have selected the specific tools that you're going to use, inspect each tool carefully. Make sure that each tool is in good condition before you use it. In addition, you may also need to prepare the work area for the pump overhaul. The work area should be cleared of all debris and other objects that might interfere with the overhaul or present a safety hazard. If the pump is relatively small, it might be easier to move it to a more suitable location, such as a shop, before you start to work on it. Before any action is taken to remove or disassemble a pump, the pump must be locked out and tagged in accordance with your company's procedures. Lockout and tag-out procedures are designed to ensure that equipment cannot operate while it is being worked on. When all of the preparations we've talked about have been made, the necessary steps can be taken to move the pump if required and disassemble it. Take some time now to answer a question on preparing for a pump overhaul. In this part, we'll watch a mechanic perform initial disassembly steps on a 2-screw rotary pump. Keep in mind that the specific steps and the order in which they're done may be different for other pumps. We'll focus on the general steps rather than on the specific details of the pump used as an example. We'll divide the initial disassembly procedure into 3 general steps: disconnecting the pump from its motor and bed plate, removing the timing gears, and removing the outboard bearing bracket. Disconnecting the pump from its motor involves disassembling the coupling that joins the pump shaft to the motor shaft. The next step is to unbolt the motor from the bed plate and swing it out of the way. If there are shims under the motor's feet, their location should be noted. Shims are important to the proper alignment of the pump and motor, and they must be put back in place correctly when the components are reconnected. If the pump is being moved, it must be disconnected from its piping and unbolted from the bed plate. Because pump fixtures such as gauges could be damaged while work is being performed on the pump, they are usually removed as part of this step. The pump in this example has been moved to a work area, and the mechanic is ready to start disassembling it. To complete the initial disassembly, he will remove the timing gears and the outboard bearing bracket. The mechanic removes the drain plug from the timing gear housing to let the oil drain out. While the oil is draining, the mechanic makes witness marks on the timing gear housing and the outboard bearing bracket. After the oil has finished draining, the mechanic reinstalls the oil drain plug. Then the mechanic loosens each of the bolts that attach the timing gear housing to the outboard bearing bracket. As each bolt is removed, he sets it aside in the parts pan. After all of the bolts have been removed, the mechanic will remove the timing gear housing. The mechanic begins by using a hammer to tap out the alignment dowel pins on both sides of the housing. Next, he removes the housing plate set screws and the housing plates themselves. Then he loosens and removes the retaining nut on one shaft and then the lock washer. He'll also remove the retaining nut and lock washer on the other shaft. When the mechanic removes the timing gear housing, he is careful to pull the housing back slowly and evenly to keep from damaging the shafts and the timing gears. He places the timing gear housing in a cleaning tray. It will be cleaned later on. After the housing is off, he removes the timing gear housing gasket. Now the timing gears can be removed. First, the mechanic removes the spacer on each shaft. After he makes a witness mark across the 2 gears so that the gears can be reinstalled properly, he uses a gear puller to move the driver gear along the shaft until it can move easily. Then he uses the gear puller to move the driven gear until it is alongside the driver gear. The timing gears are removed the rest of the way by hand and put in the parts pan. Both keys are removed from the shafts and placed in the parts pan with the gears. After that, the mechanic removes 2 washers from one of the shafts. The gear teeth should also be checked for any signs of spalling, which is flaking of the teeth. Damage to the timing gears affects the operation of the pump, and it can cause damage to other pump components. For this reason, timing gears that are excessively worn or damaged should be replaced. The final step of the initial disassembly is removing the outboard bearing bracket. The mechanic loosens the bearing bracket nuts with a wrench. After the nuts have been loosened, he can remove them by hand and set them in the parts pan. The mechanic then makes witness marks on the bearing bracket and the pump casing so that these parts can be put back together properly. Now he can separate the bracket and its gasket from the casing and pull it back off of the shafts. He'll remove the bracket gently and evenly, being careful not to bump the flange bolts, the shafts, and the mechanical seals. When the bearing bracket is removed, the mechanic places it in a cleaning pan. This completes the initial disassembly. Now try a question to see if you understand what we've covered in this part. In this part, we'll watch a mechanic complete the disassembly of a 2-screw rotary pump. We'll focus on the general steps involved in the disassembly rather than on the specific details of the pump used as an example. What we're calling the final disassembly starts with the pump disconnected from its motor and bed plate, and with the timing gears and the outboard bearing bracket removed. We'll see the mechanic remove the outboard mechanical seals, the inboard end bell, the 2 shafts or rotors, and the inboard mechanical seals. On the pump used as an example, the removal of the outboard bearing bracket exposes the outboard mechanical seals. As each mechanical seal is removed, it must be handled very carefully to avoid damaging the carbon sealing face. This surface is highly susceptible to damage from moisture and dirt, and to etching caused by acids in human skin. So, the mechanic must avoid touching the carbon sealing face directly with his hands. The mechanic measures the distance from each mechanical seal to the end of its shaft. He will need these measurements to ensure that the mechanical seal is positioned correctly when he reassembles the pump. If a mechanical seal isn't positioned correctly, the seal may not operate properly. After he takes the measurements and writes them down, the mechanic marks each seal so he'll know which shaft the seal should be put back on. Then he loosens the set screws on each mechanical seal and slides each seal off of its shaft. When each mechanical seal clears the tip of its shaft, the mechanic slips the seal into a clean cloth and sets it aside in a safe place. The mechanic can now remove the inboard end bell. This is done to expose the bearings in the inboard bearing bracket for inspection. The end bell contains a reservoir of oil that's used to lubricate the bearings, so he'll have to drain the oil first. To do this, he sets a pan directly under the end bell and then removes the drain plug. While the oil is draining, the mechanic can place witness marks on the end bell and the bearing bracket, as well as loosen and remove the end bell's nuts and bolts. After the oil reservoir has drained completely and the drain plug has been reinstalled, the mechanic separates the end bell from the inboard bearing bracket and pulls it carefully off of the shafts. He then places the end bell in a cleaning pan so that it can be cleaned before it is reinstalled. He also removes the end bell's gasket. The last components to be removed in this example are the inboard mechanical seals. As with the outboard mechanical seals, each seal is marked as to its location, and its position on the shaft is determined by measuring. After marking and measuring the inboard mechanical seals, the mechanic carefully removes each seal and wraps it in a clean cloth to protect it and keep it clean. In some cases, a pump's inboard mechanical seals are removed before the pump's rotors are removed from the casing. Regardless of whether the seals are removed before or after the rotors, however, the procedure for removing the seals is the same. With the rotors and the inboard mechanical seals removed, the mechanic has finished disassembling the pump for this example. Now try a question to see if you understand the disassembly steps that we've covered. The next components to be removed in this example are the rotors. As this is done, the mechanic must be extremely careful not to bump the rotors against the casing or the flange bolts. He must also avoid banging the rotors together or dropping them on the floor or any other hard surface. To protect the rotors, the mechanic follows three basic guidelines. First, he pulls the rotors out of the casing together. Second, he holds the rotors firmly together as they slide out of the casing to keep them from shifting. And third, he makes sure that the rotors are adequately supported until he sets them down. In this topic, we looked at some basic preparations for a pump overhaul, and we watched a mechanic perform initial disassembly and final disassembly steps on a 2-screw rotary pump. Take some time now to try a few practice questions. The pump that's used as an example in this part is a 2-screw rotary pump. As we watch a mechanic clean and inspect its components, keep in mind that the pump components you work with may be different. However, the basic principles that we'll cover will still apply. We'll start with the rotors. The mechanic will use a non-toxic, non-flammable solvent and a soft bristle brush. Even though the solvent is non-toxic and non-flammable, the mechanic is wearing safety goggles and rubber gloves. Even non-toxic solvents can irritate skin and eye tissues. Make sure that you wear the appropriate protective equipment whenever you use solvents. The mechanic uses the brush and solvent to get the rotors as clean as possible and free of foreign matter such as dirt, grease, or oil that could make it difficult to inspect the rotors. As he finishes with each rotor, he sets it on a clean, lint-free cloth. The next step is to inspect the rotors. The inspections are made with the rotors suspended one at a time on V-blocks. The mechanic has set up V-blocks that are the proper height and sturdy enough to support one of the rotors. With the rotor mounted on the V-blocks, the mechanic looks it over carefully to see if there are any visible imperfections. At the same time, he feels the rotor's surface to check for wear or damage that might not be visible. He rotates the rotor until he is satisfied that he has inspected all of its surfaces. Minor blemishes can be removed with a non-abrasive cleaning pad. If the mechanic had found any chips, cracks, or worn edges, he would have reported them to a supervisor. After using the cleaning pad, he cleans the rotor with solvent to rinse off any particles of the cleaning pad that may have remained on the rotors. Inspecting a rotor involves more than just a surface inspection. The mechanic also has to check each rotor to make sure that it is not bent or out of round. These checks can be made at several points along the length of the rotor using a dial indicator. To check each rotor, a dial indicator is mounted so that its stem presses slightly against the surface of the rotor. After setting the dial indicator to 0, the mechanic rotates the rotor as he watches the face of the dial. If the pointer moves slowly away from 0 and then back again, the rotor might have to be replaced, depending on the rotor's specifications. If the pointer flickers very quickly at any point, there could be a burr or a dent at that location. Small burrs or dents can be removed without having to replace the shaft. In our example, the mechanic finds no problems with the rotors, so he moves on to clean and inspect the mechanical seals. After he finishes cleaning the seals, he will inspect each one for signs of pitting, etching, or other surface damage. Then he cleans the bearings that he removed from the timing gear housing. He'll also clean the bearings that remain in the inboard and outboard bearing brackets. When he's finished cleaning the bearings, he'll inspect them to make sure that they're free of foreign material and that they're not chipped, worn, or otherwise damaged. Any imperfections in the seals or the bearings would be reported. When he finishes cleaning and inspecting the seals and the bearings, the mechanic cleans and checks the other pump components that he removed. If he finds any worn or damaged components, he will set them aside and request replacements. After the mechanic finishes cleaning and inspecting the other pump components, he uses a cloth that has been soaked in solvent to clean the inside surface of the bore. The bore is the precisely machined chamber in which the rotors turn during operation. Then the mechanic uses a dry, lint-free cloth to dry the bore. This also removes any traces of oil or dirt that might have been missed during cleaning. Once the bore is clean and dry, it should be inspected for damage. For example, there could be scoring, gouges, or other marks on the bore's inside surface. Bore damage can result when the timing gears or the bearings fail. Also, dirt or abrasives in the fluid being pumped can result in scoring and other forms of damage. In addition, the rotors could bang together during operation and damage both themselves and the bore. If the mechanic had found any imperfections in the bore, he would have reported them to a supervisor. The mechanic also checks the pump's suction and discharge flanges for pitting, erosion, and other signs of wear. And he checks all of the pump's internal passages for signs of plugging. Next, the mechanic loosens and removes the flange bolts from the pump. The mechanic then checks the flange bolts to make sure that their threads do not show signs of damage or abnormal wear. Next, he dresses the flanges and the casing ends with a lubricated stone. This is done to remove blemishes and form a smooth, even surface that will allow a proper seal. As the mechanic stones the suction and discharge flanges and the two ends of the casing, he is careful to remove no more material than is absolutely necessary. This completes the cleaning and inspection of the pump components. Now try a question to check your understanding of what we've covered in this part. The mechanic also checks the pump's suction and discharge flanges for pitting, erosion, and other signs of wear. And he checks all of the pump's internal passages for signs of plugging. Next, the mechanic loosens and removes the flange bolts from the pump. The mechanic then checks the flange bolts to make sure that their threads do not show signs of damage or abnormal wear. Next, he dresses the flanges and the casing ends with a lubricated stone. This is done to remove blemishes and form a smooth, even surface that will allow a proper seal. As the mechanic stones the suction and discharge flanges and the two ends of the casing, he is careful to remove no more material than is absolutely necessary. This completes the cleaning and inspection of the pump components. In this part, we'll watch a mechanic reassemble a two-screw rotary pump. Although the pumps you work on may be different, the basic principles we'll cover will still apply. Just make sure that you follow your company's specific procedures. Before you start to reassemble a pump, you need to make some preparations. These preparations include 4 important steps. First, check the pump manufacturer's manual to see if there are any special precautions or procedures that apply to reassembling the pump. For instance, you might have to reassemble components in a particular order, or you might have to check specific clearances after the pump is reassembled. Second, make sure that all replacement components have been ordered and received. When replacement components arrive, inspect them carefully. You may have to use precision measuring tools such as feeler gauges or dial indicators to make sure that the replacement components conform to the manufacturer's specifications. Another preparation step is making sure that all of the disassembled pump components are gathered together and have been thoroughly cleaned and inspected. And finally, gather all the tools and materials that you'll need for the reassembly process. All materials, such as gaskets and lubricants, should be of a type recommended by the manufacturer. Gaskets must be compatible with the fluid to be pumped, and they must be the correct thickness. This mechanic has completed all the necessary preparations, and he's ready to start reassembling the pump. He'll begin by installing the flange bolts that he removed earlier. The next step is to replace the mechanical seals on the inboard end of both shafts. To make sure that the seals are positioned correctly, the mechanic relies on measurements that were taken during the pump disassembly. These measurements are used to place each mechanical seal the proper distance from the end of its shaft. After the mechanic puts each mechanical seal in the correct position, he tightens the set screws that hold each seal in place. He is extremely careful to keep dirt, moisture, and skin acids from contacting the sealing surfaces. The rotors are installed next. Before the mechanic inserts the rotors into the casing, he uses a clean, lint-free cloth to apply a coating of clean, light oil to the entire inside surface of the bore. As he installs the rotors, the mechanic makes sure that they're properly aligned with each other. He holds them close together and is careful not to bump them against the lip of the casing. He does not slide the rotors all the way in so that he can install the outboard mechanical seals. The outboard mechanical seals are installed in the same manner as the inboard seals. After he's sure that the seals are in the correct positions, he tightens the set screws that hold the seals in place. Once the outboard mechanical seals have been installed, the mechanic slides the rotors the rest of the way into the pump. After the rotors are in place, the mechanic installs a gasket over the flange bolts on the outboard end of the pump. The mechanic moves on to installing the outboard bearing bracket. He begins this step by lubricating the flange bolts. The flange bolts are lubricated to prevent the bearing bracket nuts from binding or wearing away by friction as they're turned, to help prevent corrosion, and to make later removal of the bearing bracket nuts easier. Only a lubricant recommended by the manufacturer should be used. The mechanic carefully guides the outboard bearing bracket and its gasket over the flange bolt threads. When the bracket is against the end of the casing, he installs the top two bearing bracket nuts and makes them finger tight. These two nuts will hold the bracket in place while the alignment dowel pins and the other bracket nuts are installed. Before he puts on any other bracket nuts, the mechanic inserts an alignment dowel pin into a guide hole in each side of the bracket. He then uses a small hammer to tap each pin until it fits snugly into position. When the bracket is properly lined up with the casing, the mechanic installs the remaining bracket nuts finger tight. The mechanic follows the pump manufacturer's recommended tightening procedure to tighten the nuts in a cross-torque pattern using a torque wrench. Here's an example of a cross-torque tightening pattern. The numbers on the pattern correspond to the order in which the nuts should be tightened. Using a pattern like this one and a torque wrench helps the mechanic ensure that the gasket is compressed evenly and that a tight seal is formed between the bearing bracket and the pump's casing. The next part of the reassembly procedure is reinstalling the timing gears. To ensure that the timing gears seat properly and that there's no dirt or grit on the shafts to interfere with the timing gears or the bearings, the mechanic uses a non-abrasive cleaning pad to clean the shafts down to the bare metal. Since using the cleaning pad can create tiny particles that could work their way into a bearing, he then cleans the shafts thoroughly with solvent. He then dries them with a clean, lint-free cloth. Next, the mechanic lubricates the areas of the shafts where the timing gears will be installed. He does this by rubbing them with a cloth that has an approved lubricant on it. After that, he reinstalls the two washers that he removed earlier. Then he sets the keys in the keyways on both shafts. Next, he installs the timing gears. He makes sure that he slides them onto the shafts together to avoid damaging the gear teeth. He matches the witness marks to make sure that the gears are properly aligned. And he positions the keyways on the inside diameter of the gears to match the positions of the keys on the shafts. After the timing gears are in place, the mechanic installs the spacer on each shaft. Next, he installs the bearings in the timing gear housing. Then he installs the timing gear housing with a new gasket. To secure the timing gears in position, the mechanic slips a lock washer into place against the spacer on each shaft and then finger tightens a retaining nut against each lock washer. He uses a hammer and a pin punch to fully tighten both retaining nuts. An ear of each lock washer is folded against a groove in the edge of the corresponding retaining nut. After installing the timing gear housing plates, he tightens the set screws that hold them in place. The last component to be installed is the inboard end bell. The mechanic carefully slides the end bell and its gasket over the two shafts. Then he installs the nuts and bolts that hold the end bell in place. He tightens them until they're finger tight. Then, as he did before, the mechanic uses a torque wrench and a cross torque pattern to tighten the nuts and bolts to make sure that the gasket is evenly tightened and that a tight seal is formed between the end bell and the inboard bearing bracket. After the pump is completely reassembled, the mechanic turns the rotors to make sure that they turn freely without rubbing. This pump is not being returned to service right away, so the mechanic does not have to fill each oil reservoir. He'll finish his part of this job by picking up his tools and making sure that the work area is clean. Try a question now to make sure that you understand the material that we've covered. In this topic, we watched a mechanic clean and inspect the components of a 2-screw rotary pump, and then we saw him reassemble the pump. Take some time now to try a couple of practice questions. Before any action is taken to remove or disassemble a pump, the pump must be locked out and tagged in accordance with your company's procedures. Lockout and tag-out procedures are designed to ensure that equipment cannot operate while it is being worked on. Several tasks need to be performed before the timing gears can be removed. First, the mechanic removes the spacer on each shaft. After he makes a witness mark across the two gears so that the gears can be reinstalled properly, he uses a gear puller to move the driver gear along the shaft until it can move easily. Then he uses the gear puller to move the driven gear until it is alongside the driver gear. The timing gears are removed the rest of the way by hand and put in the parts pan. To protect the rotors during their removal, the mechanic follows 3 basic guidelines. First, he pulls the rotors out of the casing together. Second, he holds the rotors firmly together as they slide out of the casing to keep them from shifting. And third, he makes sure that the rotors are adequately supported until he sets them down. Inspecting a rotor involves more than just a surface inspection. The mechanic also has to check each rotor to make sure that it is not bent or out of round. These checks can be made at several points along the length of the rotor using a dial indicator. To check each rotor, a dial indicator is mounted so that its stem presses slightly against the surface of the rotor. After setting the dial indicator to 0, the mechanic rotates the rotor as he watches the face of the dial. If the pointer moves slowly away from 0 and then back again, the rotor might have to be replaced, depending on the rotor specifications. If the pointer flickers very quickly at any point, there could be a burr or a dent at that location. Small burrs or dents can be removed without having to replace the shaft. When a mechanic installs timing gears, he should make sure that he slides them onto the shafts together to avoid damaging the gear teeth. He should also match the witness marks to make sure that the gears are properly aligned. He should also position the keyways on the inside diameter of the gears to match the positions of the keys on the shafts.